In this video, we'll discuss an introduction to the Scheme programming language and its basic syntax. But first, let's place it in a bit of a historical context here. So back in the 1930s, there was a big push among mathematicians to figure out what exactly is computability, or what does it mean for something to be computable. And a number of formalisms were developed, including Alan Turing's Turing machine and Alonzo Church's the lambda calculus. But ultimately, the Church-Turing thesis proved that all of these different formalisms were equivalent. They're all saying the same thing. And the term became Turing complete. So if I have one formalism that's considered Turing complete, that means it can compute all the same things as all of the other equivalent formalisms. And this became our definition for computability. The thing that's being computed, or the class of problems that can be computed by all of these equivalent formalisms, was considered computation. Now, Turing machines define computation as transitions of states and an infinite store of values. And this led to the idea of imperative programming. On the other hand, the lambda calculus represents computation as a sequence of intricate symbolic substitutions. So think we have a function with a bunch of arguments. Those arguments get substituted into the parameters of some function. And this led to what's known as functional programming. So in the 1950s, John McCarthy created the Lisp programming language as an implementation of lambda calculus. So lambda calculus before this point was essentially just a mathematical theorism, but in the 1950s it actually became a programming language. And computation in this Lisp programming language was done by substituting parameters as, say, function applications. And the output of a program was then just a functional translation of its inputs. So the key features of Lisp was that it had functions as data, had an emphasis on recursion, had garbage collection, well ahead of many of the modern languages that now have taken it as default. And it had what's known as side effect-free programming. So the functions in Lisp were known as pure functions. They're input to output mappings with no mutation of any external state. Which it does a lot of nice things. We'll talk about them as we go through the course, but in a nutshell, it simplifies debugging because there's fewer causes of errors, and it supports concurrency very well because the order of valuation is oftentimes irrelevant. If we have two functions that are going to compute the same thing no matter which order they run in, then it doesn't matter if one's running before the other because their actual execution won't affect each other. So a lot of useful features in the Lisp programming language. Now in this course, we're going to be learning Scheme, which is a dialect of Lisp. Essentially, it's the basic Lisp combined with some of the Algol features. Algol being, again, one of those early languages. Some of the nice features that it brought into to Lisp was block structure for the language and lexical scoping, things that we'll talk about in the lectures to come. And it enables what's known as lexical closures, which are a great way of having reusable and modular code. Now, Scheme itself has a nice minimalist design principle. It's one of the reasons I choose it for this course, because it gets us down to the nitty-gritty essence of the language itself without all the bells and whistles getting in the way. So it's going to give us a nice close look at building the complexities that come into a language starting from scratch. So let's get into it. Let's talk about Scheme syntax. So for this course, we're going to be doing all of our programming, or at least I will be on the videos here, doing all my programming in the Dr. Racket IDE. So Dr. Racket is freely available online. Check the main course page. You'll see a link there. Installation should be relatively straightforward. I recommend doing so now. Pause the video, make sure you have it installed, and we'll go forward from there. Once you have the program installed, you can get it up and running here, Dr. Racket. And you should get something that looks relatively like this. Now, before we do any sort of programming, Dr. Racket is it's an IDE for all sorts of variants. Racket itself is a superset of the Scheme language. It has a bit more features, but it's built out of Scheme. So the IDE here needs to be told what language specifically to choose. So down at the bottom left corner, you should see something that says determine language from source, I believe is the default. If you click that and go to choose language, you should get a window that looks like this. And this is a list of all the languages in the Dr. Racket IDE. We'll be using R5RS, which stands for the Revised Fifth Report on the Algorithmic Language Scheme. So this is the short form for Scheme. So if you click on that and go to Show Details, it'll open up another panel here. And down at the bottom, all this is going to stay the same except this very last one here, Initial Bindings. By default it says disallow redefinition of initial bindings, which means if something already exists, like say a max function in the scheme language, we won't be able to define our own. So we're going to uncheck this box. This will let us reinvent a few wheels so that we can help learn how wheels work. And click OK, and you should see R5RS custom down at the bottom, and we're good to go. All right. So the IDE itself is divided into two main areas. So let's talk about this bottom area first. This is known as the REPL area, or the read eval print loop. And this essentially is just the scheme interpreter is waiting for some sort of scheme code, one expression at a time. It's just going to tell us the value of those expressions. So every expression has a value with very few exceptions. So very quickly I could say something like the expression 4, it has the value 4. We can ignore that. There we go. The expression 4 has the value 4. If I do something like plus 1, 2, 3, talk about the syntax in just a second, that has the value of the sum of those three things. Or if I say display hello world, like so, then it displays hello world. All right, that's pretty much that. The display function here is the only thing that we've seen so far. One of the main things we'll see throughout the entire course, actually, that doesn't have a value. In this case, it's used for its side effect of displaying some text to the screen. So this comes out in a different color here. This is standard output, whereas this is the value of some expression. All right. One other thing, you can press Control up to get old commands back, which is quite useful. Saves you from having to type things multiple times. Okay, so that's the REPL area. This bottom area is used for small snippets of code. We can just punch values in or punch expressions in and get their values back. At the top here, we have the definitions area, and this is for editing large blocks of code. Allows saving, loading, compiling, running, that sort of thing. So we can put in some code here, plus 1, 2, and hit enter, and it just goes to the next line waiting for more code. So we'll say display hello scheme. Hit enter and nothing happens. Now if we want something to happen, we have to click the run button, or you can hit Control R to run. We hit run, notice the REPL refreshes, and we have just the output now from our display here. So in this case, it tells us the value of things that are floating out in the global space. We'll talk about scopes in a bit. So for example, plus 1, 2 tells us the value is 3, and it says hello scheme, and it displays hello scheme. Okay. All right. So that's the basics of the IDE. We'll get a lot of familiarity with it. There's lots of other hotkeys and stuff. You can make it a dark theme somehow in the settings, somewhere in the view now. Feel free to spend some time familiarizing yourself with it. We will be using it extensively this term. Now, on to other stuff. First things first is comments. So there's two kinds of comments you can use in Scheme. The default Scheme comment is a semicolon. So this is a line comment, or an end of line comment, if you will. If I have new code down here, like the value 3, it's no longer commented. So you can see with the lighter color there, comes through as a comment. Technically as well, you're allowed to use multi-line comments. So this is a block comment on multiple lines. And that's the hashtag pipe, and then whatever you want, and then pipe hashtag. A bit like */ /* from C and other Java languages. But in this case, slightly different syntax. Now that's actually technically a Racket comment, but since we're in Dr. Racket, it doesn't care which type of comment we use, and it assumes that it's a comment. Just be careful if you're taking your Scheme code elsewhere. Using block level comments like this might make it less transferable. All right, so comments pretty straightforward. Let's go about primitive values next. So let's go back to our notes here. So primitive values come in a bunch of different flavors. So we have numbers, first of all, which come in, again, a number of varieties here. So let's actually go back to our code here. So first off, we have numbers like integers, like 486, the value of which is just itself. We can have real numbers or floating point numbers like 3.1415926535889. And that's just itself, which is nothing new, hopefully. In Scheme, we can have what's known as rational numbers. So rational numbers, just two integers over a divisor. And that actually keeps it in its exact form. So 1/3 is 0.333333 repeated to infinity. But if we don't have to express it in decimal form, we can keep it in the exact value, 1/3. All right. You can also have very large and very small numbers using scientific notation, so 10.321 exponent to the negative 20. So E here specifically says for the scientific notation. It's not used for regular exponent math. It's for representing scientific notation numbers. So notice I punched in 10.321. It moved the decimal point, so it's in proper scientific notation. We have 1 dot and then all of our specific values, and then exponents at negative 19 now. So very large, very small numbers there. We can also do complex, so imaginary numbers like the square root of a negative value. Notice it's the square root and then an I for imaginary. We won't be using that very often, but it's good to know that these things are available. All right. So first primitive type, numbers, many different kinds of numbers out there. The next primitive type is Boolean values. Boolean values are straightforward. There's not too much trick. The key words for them, though, are hashtag true and hashtag false, or octothorpe T and octothorpe F. This means true and false values as they would in any other language. There's also available the string type, so you could say hello world, and the expression of that is as we'd expect it, just the string itself. Okay, that's the primitive values. There are other kinds of values, other types of values, characters. We'll talk about symbols later on, as well as pairs and lists, which are more complex types. But for now, let's just stick to the basics: numbers, booleans, and strings. All right. Now, once we have all of these things in a given format, let's say once we have values, it's oftentimes useful if we want to compute things to combine those values. Let's talk about combinations next. So a combination is essentially it's some sort of expression that combines all of these things. Let's start first off with arithmetic. So the general syntax of all of the combinations can be seen in the notes here is some operator followed by a number of operands, all wrapped inside round brackets or parentheses. Okay. We'll talk about all the different parts of that in just a second. They're all very important, but it's within parentheses, it starts with the operator, and then it goes through the various operands one after the other. So for example, if we want to do some addition, as we saw before, we can say plus 1, 2, 3, 4, 5, 6. Oops. And that says bring these three things together. The operation addition along with the two input values 1, 2, 3, and 4, 5, 6. Combines them and tells us the value of that addition. Okay. So the value of a combination is the result of applying that function to its arguments. Let's see a couple other examples while we're here. So for example, we want to have negation, subtraction. We could say minus 4, 1, and that specifically means 4 minus 1, not the other way around. So you can think in your mind, we take this symbol and we move it in between as we're normally used to seeing the infix notation. Okay. One other one here, just to see how things happen. If I say divide 3 by 2, you might expect that's 1.5, but because we have rational number type in the language, it actually expresses it in a more exact form, 1 1/2. Okay. Now, it's important to mention that the brackets that we're seeing, the parentheses here, are significant. Okay, they're not just saying do this first. They can be used for a similar reason, but the main purpose of a bracket here is to denote that a function is going to be applied, like a function application or a function call. Okay, so for example, if I say plus 1, 2, that says take the function addition and apply it to the arguments 1 and 2. Okay, so 1 plus 2 gives us 3. But if I said, for example, with two brackets, plus 1, 2, that says take the operation addition, apply it to plus 1, 2, and then the result of that, which is 3, is now being considered as a function, right? So if I run this, we get an error. The error is the application was not a procedure. We were given 3. We were expected a procedure, but we got the number 3. So what happens essentially is if I have plus 1, 2 like this, scheme starts from the inside here and says, okay, well that's 3. And now we have bracket 3, which says take the function 3 and apply it to its no arguments, which doesn't make any sense, and hence we get our error. Similarly, if I were to say plus 1, 2 without brackets, you might think this is also 3 just because in Other languages, like Python, for example, we could say 1 plus 2, and it would give us back the value 3. In Scheme, if I say plus 1, 2 with the prefix notation, it actually just says, okay, here's 3 different things. You haven't asked me to do anything with them separately, so here's their values. This plus symbol refers to the procedure that does addition. The 1 is a 1, and the 2 is a 2. So there it is. There's the values of those 3 things. What's next is what Scheme says back to us. So it's not super helpful in that case. So it evaluates all 3 things individually. If you want to combine them, use parentheses. All right, so let's see a few of the other built-in operators. It has to go somewhere in the notes, so it may as well go here while we're talking about the basics. So all the standard arithmetic operators are available. So we've seen plus 1, 2, for example. Move my mouse here. We've seen plus 1, 2. I could say, caps lock's on. I could do something like times, I guess, times 3, 4. We've already seen divide. Divide 1, 2 gives us a half. And subtraction we've already seen as well. Some of the other useful operations like absolute value. So ABS of -3 gives us back regular 3. If you want to do exponents, it's EXPT for exponent. And say 2 to the 8, for example. So 2 to the power 8 is 256. We could do square root. So SQRT of 25, for example, gives us 5. And if we want to do modulus, the keyword is modulo. Modulo 13, 10. So that's 13 mod 10. So 10 goes into 13 once with 3 remainder. So we should get 3. Okay. So there's a bunch of other arithmetic operations we may see as we need, but there's the important ones. We can do some relational operations as well. So for example, if I want to know if 2 things are the same, I can say equals 3, 3. Now the equals sign in other languages means assignment. Here it is asking equality. It's like double equals in other languages. In this case, 3 does equal 3. Yeah, so note very carefully, this is for numbers specifically. If we want to know equality between 2 numbers, just the single equal sign. All right. We can do other relations like less than, so less than 2, 3. Now this might be odd because, or it might feel odd at least, because the comparison is on the left-hand side, not in between. So if you're conditioned to think, okay, the small side or the pointy side of the arrow points at the smaller one, you can't do that anymore unless you want to do it in your mind. Take this symbol and mentally cut and paste it in between things, and it becomes a more obvious operation. Otherwise, just remember that this means less than, and now we're asking, is 2 less than 3? And if we want to do greater than or equal to, it's greater than or equal to, we'll say 5 and a 5, and that's true as well. All right. You can also do greater than and less than or equal to, as you might guess. Next, logical operations. So the basic logic operations and, or, and not are just themselves. So if I want to say and, true, for example, that's going to be true. I want to say or, say false and false, gives us false. And the not operation, not true, is false. It's worth pointing out, I suppose, at the beginning here that these, that and or at least, are short circuit operators, which means they'll stop processing as soon as the answer is obvious. So if I said something like and false and then a garbage term, something that doesn't exist, a variable that we haven't defined, okay? This comes up as false because as soon as we have false and anything, the whole answer has to be false, so it doesn't even have to look at this garbage term, which normally would be a syntax error trying to use a variable that doesn't exist. Okay, so short circuit operators, they're a bit optimized in terms of what work actually gets done. Okay, let's move on then to prefix notation in a bit more detail here. So we've seen now that if we want to combine pieces of information, operations and operands, what we need to do is put things within parentheses in the specific prefix order. Let's say the operation comes first and then the list of arguments. Now, there's a bunch of reasons that we want to use prefix notation over other types of notation, like the more familiar infix notation. The main advantages are, first off, we can have an arbitrary number of operands very easily expressible in a given expression. So for example, if I wanted to multiply together a bunch of values, I can say times 4, 5, 6, 7. Okay, and that just says multiply all of these things together. Take this operation and apply it to all 4 of these operands. So you get 840. Now, just to give you a sort of heads up to what this means in terms of operators that have a specific order to their operands, this works very similarly to what you would see in infix if we had taken this value out, sorry, the symbol out, and placed it in between each one of the arguments here. Okay, so if I said minus 10, 2, 3, 4, it means essentially 10, minus 2, minus 3, minus 4. Let's put that back. So 10 minus 2 minus 3 minus 4 is 10 minus 9, should be 1. All right, so we can have an arbitrary number of operands. Operator is always going to be on the left, and then the whole combination is limited by brackets, so we know exactly which arguments go to which operator. But we can also very easily nest these operations. So for example, I can have one operation just easily placed inside another, like plus, and then another plus, 1, 2, 3, and we'll say times 4, 5, and a 6. So this says, add the result of this addition, which should be 6, to the result of this addition, which should be 20, to whatever the value of this expression is, which is just 6. So 32. So add 6 plus 20 plus 6, 32. There we go. So it's very easy to nest these things because we just essentially combine them in the same way. There's no ambiguity that arises. Okay, and it avoids issues of precedence and associativity as well. So for example, consider the following expression in infix. If I said 15 minus 10 divided by 2, the answer here is a bit ambiguous. It requires a few extra rules in order to figure out what the actual meaning of this expression is, right? We have to have precedence rules added on top of this expression, sort of a hidden logic to figure out what this value is. Right? We have to know that we do 10 divided by 2 to get 5, and then we say 15 minus 5 to get 10. If we didn't do that, we might think left to right, and we'd say 15 minus 10 is 5, and then 5 divided by 2 gives us 2.5. So depending on the order, we get different answers. And we have to have these extra rules of precedence in order to figure out the correct answer. Using prefix notation, there is no such ambiguity. It would be just minus 15 divide 10, 2. It just takes one value, subtracts it from the result of combining these other things here. So because we have brackets around every combination, the nesting is explicit. It tells us which operations happen first. We can't say 15 minus something until we know what that something is, so we have to calculate 10 divided by 2 first. Okay, and in that case we get, get our answer there. If we want to do the opposite way around, we'd say, was it minus 15, 10 divided by 2? So it'd be minus 15, 10, and then all of that, divided by 2. Okay, so it says do the subtraction first and then divide the answer, and we get the other answer, 2.5. All right, last main advantage of using prefix notation, actually just go to the slides for the example here, is that there's no limit to the depth of nesting. So we can have combinations that nest quite easily. I'm actually just going to put this up in block code here. I have combinations that nest quite easily. So we have plus all of this with the result of all of that. In order to figure out all these, we could walk through the brackets and do each individual math without ambiguity. Maybe a bit of say consternation trying to figure out what this thing actually says, but there's no limitation on the depth of nesting. If we want to understand these things a little better, though, it helps to use some pretty printing. Now, the convention for pretty printing is to align operands vertically if we have a long combination. So for example, this plus symbol has two operands. It has this expression and this expression. The result of those two things need to be added together. So if we want to make that very clear, we can line them up. And it's the default in in Dr. Racket, you just hit enter, and it will line up the operands vertically. So for example, if I want to line up the operands for this multiplication, I go to here, and I hit enter, and that lines up. And similarly, let's line those up as well. And now you can very clearly see this plus symbol is going to take all of this with all of that. This multiplication symbol is going to take the result of this with all of that. And this plus symbol is going to take all of the result of this and the result of that. So it's a bit clearer to see. Once it's not just math symbols, it'll actually become a bit easier to read as well. All right, so let's do a little bit of practice here. Let's run our code here first. There we go. So it runs fine, no issues there. A little bit of practice. Now, if this were a face-to-face lecture, I'd actually be asking you guys for the answers to these things. So when I do some practice, I recommend pausing the video after I post the question. Try to work through it on your own, then unpause the video and compare your answers and try to evaluate why you got it right or how you got it wrong. Okay, so what I'm going to do here is write something in infix notation, and we're going to then convert it into prefix notation. So a good start to get practice with this stuff. So I'm going to put a comment here, 7 minus 4 times 10 plus 12. So pause the video, see if you can turn this into an infix notation, so something like we had in the lines above there, and we'll go from there to see how this works. Quick second, Welcome back. So let's try and solve this out. Now there's a bunch of different ways you can do this. It's important to notice that bedmess, or precedence, needs to be imposed on this expression in order for it to be unambiguous. So what we want to do is start with the first operation that would happen in terms of infix notation, or in terms of the normal precedence rules, and work our way outwards from there. So what's the very first thing that's going to happen in this combination? We have subtraction, multiplication, and addition. So by precedence rules, the multiplication will happen first. So 4 times 10 is the very first operation that should occur. So we'll say times 4 and 10. Put them in a nice tight combination right next to each other. No ambiguity there. Now what we do is take the next operation. So after we say 4 times 10, the next thing that would happen would be left to right, since plus and subtraction have the same level of precedence. We go from left to right, and the subtraction is next. So that says 7 minus the result of 4 times 10. So we'd say minus 7 and the result of 4 times 10. And again, because we have the subtraction symbol, it's very important that the 7 comes to the left, or as the first argument of the subtraction operation. So it goes to the left of the second argument. All right, and then there's only one operation left after that, so we'll wrap that in one more set of brackets here. So we say plus all of this and 12. Now technically it doesn't matter which side the 12 goes on, because plus symbols don't care about that sort of thing. All right, so there's our combination. You can work this out on a calculator to figure out what the value is, and then we'll run it to verify. Code didn't crash, so I'm going to say it worked. Let's move on to another example, a bit bigger one here. Okay. So we got 6 divided by 3 plus 9 times 2 minus 7 plus, then in brackets, 3 plus 4 times 2. All right. So again, pause the video, try to work through it, and welcome back. So what's the first operation to happen here? Well, with precedence, we have multiplication and division are going to happen before addition and subtraction, but even before that, we have exponents. There's none in this expression, and brackets. So brackets happen first. So this combination here is going to be the first one. We got 3 plus 4 times 2. So 2 operations in there, and the multiplication is going to be the first one that occurs. So we're going to have times 4, 2 is the very first thing. And then because that's all still within the brackets, the next thing is we add the 3 onto that. So plus 3, and then the result of that. Quick hotkey note, if you hold Alt and press left to right, Alt on a Windows keyboard at least, it's probably Command or something crazy on a Mac. If you hold Alt and press left to right, it'll jump from the front bracket to the end bracket. It's an easy way of jumping from one combination to the next. All right, so the first thing that happens, times 4, 2, and then we add the 3 to that, and what we have left is we need to combine all of this to that value. But the plus symbol isn't the next thing that happens. We have to get rid of the division and the multiplication first. So technically the next thing that happens is 6 divided by 3, and that has nothing to do with this 3 plus 4 times 2 at the end. So I'll put some spaces in between these, and we'll do 6 divided by 3, or divide 6, 3. Okay, so that gets rid of this combination. The next thing that happens is 9 times 2, again, sort of independently so far. So we'll say times 9, 2 in the middle here. Okay. And then walking through this, so we got the division, the multiplication. Next things through is all plus and subtraction. So let's do the first plus symbol here. That's going to combine these two blocks. So let's go to the front here and say, plus, and then all the way to the end and close that combination. So now we have this represented by the front, and we have all of this represented at the end. So we just need to get that -7 plus all of that in there. Okay, so the next thing we could do here is, let's do the -7, I suppose. So it's all of this minus 7. So we'll put a minus at the front. Oop, jump to the back of that, and it's not working. There we go. And put a 7 there. So all that minus 7. And then finally, we're just joining the two pieces together. So plus all of this and all of that. Run our code, and we get the answer that I have written down. So that's a good sign. Now, it's worth pointing out that there is potentially more than one answer to these things. In particular for this example, because the arithmetic operations can take multiple arguments, more than 2. In this case, we could actually express that top level addition, or we could express all these individual parts being added together. So this is 6 divided by 3 plus 9 times 2 plus -7 plus the result of all those things. So we could write this a little bit differently as plus divide 6(3) times 9(2), the value -7, or if we want the function negate 7. And what's the last one? All of this combination here. Plus 3 times -4, or sorry, plus 3 times 4(2). Okay, so the reason being there, because plus can take multiple operations, we're just going to take all of these pluses out and say they're all saying the same thing. So we'll just put a single operation, and then argument 1, argument 2, argument 3, and argument 4 for one big plus operation. And if we run this, we should get the same answer twice. There you go. So it goes to show that there's more than one answer to many of these problems. All right, it's good for practice. Let's move on now to evaluating combinations. So kind of already know how to evaluate combinations because there's sort of an innate knowledge, or at least hopefully a grown knowledge of how to do arithmetic combinations. Right, if I give you a bunch of operators and a bunch of numbers, we can work through it, reduce it down to a single value. So the question is, how do we actually evaluate these things, right? How does +1, 2 get combined to get the value 3? Or how do these more complex versions get reduced down to a singular value? There needs to be a sort of general rule for describing these things, a nice consistent pattern that we can follow, so that even if we don't know the answer, we could explain it to a computer, and the computer can figure out the answer for us. So let's go to our notes here. Evaluating combinations. There we go. Right. So the general rule of evaluation can be broken down into 2 steps. There's a general rule of evaluation. The first step is to evaluate all of the sub-expressions of a combination. And then secondly, we want to apply the operator to its operands. Now these steps are a bit recursive, right? The base cases of the recursion are going to be the primitive values. So if I ask you to evaluate the number 3, for example, that doesn't require any further evaluation. It just knows the value is 3. So primitive values like 3 already have an answer. Similarly, if we have a primitive operation, so if I said something like, what's the value of plus? It's just the procedure plus. It doesn't have to do additional work to figure out what that means. There's no additional combinations to determine a result. It just says this symbol represents that operation. Okay. Now the recursive cases are when we have nested expressions. So if I have something like this combination here, in order to do this addition here at the top level, I have to evaluate all of the sub-expressions. So if I call some evaluate function on the top level expression, that evaluate function will have to call evaluate on this, and on this, and on this, and on this. It'll get a bunch of numbers out of that, and then it can finally apply the plus to all of those numbers. Let's go through an example here. It's going to feel like I'm driving this into the ground a little bit, but that will be very useful later on when this stuff gets complex, and we're going to make this rule a little bit more involved. But this is the general rule of schemes evaluation. It's going to be used throughout the course, so it's a good idea to get a strong handle on it now while the examples are easy. So for example, let's evaluate this combination here. So times +2 times 4, 6, and a +3, 5, 7. I think I have a tree already in the notes for this. Save me a bit of time here. Oh, here it is. So here's our evaluation expression. So if we want to evaluate this, we have to evaluate all of the combination as a whole first, right? I say evaluate this full expression. And now the general rule says to do that, I need to evaluate the sub-expressions. So the sub-expressions here are the operator, this first combination, and this second combination. Okay, so at the top level of our tree, we have all of the expression, and that gets broken down into the sub-expressions. For each one of those sub-expressions, we call this evaluate operation again. This asterisk symbol then means multiplication. If we go to Dr. Rackett, we can ask, what's the value of multiplication, or the asterisk, sorry, and it says it's the procedure times. Okay. But to evaluate these other combinations, like plus 2 times 4, 6, well, those are still complex combinations, so we need to reduce them down a little bit further. So again, we say, what are the sub-expressions? We have the operation plus, we have the value 2, and we have the combination times 4, 6. So we evaluate each one of those in turn. Plus means addition, 2 just means 2, and times 4, 6 is a combination. So we walk through the sub-expressions, times 4 and 6, evaluate each one of them in turn. They're all primitive values or operations, so there's no further work that needs to be done. We can finally apply those things. So we create this tree by calling evaluate over and over and over again. Once we have it down to a point where we're at these primitive values, we can start to combine these things back. So times 4 and 6 will give us 24, so this combination can be replaced by its value. We have plus 2, 24. Then we can do that addition, so we get 26. Now we have times 26 and whatever the value of this other side is. And we can walk through that in the same manner. Okay, so this is the general rule for evaluation. I don't think there's anything else I need to say about that. Okay. So as I said, this might seem like overkill for now, but this simple rule here, just for evaluating these expressions, will actually be a general rule of all computation throughout Scheme as we learn more about Scheme. But let's get back to some practice now. Let's figure out what's the output of a bunch of pieces of code before we get to symbolic abstraction. Save that for the next video. So I'm going to run this here just so that our code is a bit clean. It's a bit bigger so we can see stuff. Okay. And again, if this was a face-to-face lecture, I'd be asking you guys, what's the value of all of these? So I recommend I'm going to type something in. I'll give it a small second, pause the video, see if you can figure out what the value is, and then run it yourself and see what the actual answer is. So let's start off easy. If I type in 2, 3, 4, what is the value of this expression? So this one's not a trick question, it's just an integer, so we get 234. What if I type 234 in brackets? What's the value of this expression? So if I run this, we actually get an error. Again, the reason this is an error is because brackets in Scheme they're significant. They mean function application. They say, take this operation and apply it to its operands. Now in this case, we didn't give it an operation. We gave it an integer. You can't apply an integer the same way you would apply a function. It doesn't really make sense, and hence we get an error. Expecting a procedure, but we got a number. Okay. We've already seen this. Plus 3, 4. So this is asking Scheme to evaluate all three things individually, so the procedure plus the value 3 and the value 4. If we don't include the brackets, it says, well, I don't know to combine these things, so I'm not going to assume to combine these things. Okay. How about this expression? All right. If we run this one, we get another error. Similar error to what we saw before. So in this case, there's no space between the plus and the 3. So the value of plus 3 is just 3. It's positive 3. So this means, again, we're trying to apply the procedure plus 3, which doesn't exist. It's just an integer, to the argument 4. So I don't know where that 4 would go because there's no parameters in the value 3. So the whole thing doesn't make sense and we get an error. All right. And then the correct way of doing this, plus 3, 4. Hopefully you'll agree we get the value 7. I can make this a bit trickier. What if I say plus 3, 4? Okay. So plus 3, 4 in this case, we've seen this before. This is going to be an error. Again, the error says application, not a procedure. We're expecting a procedure, but we got the value 7. So what this says is evaluate this inner part. That's a properly formed combination, plus 3 and 4. Take the plus operation, add it to the arguments. But what we get back is the number 7, and then we wrap 7 in a new set of brackets and say run this as though it were a procedure, but it's not a procedure, it's an integer. Okay. And how about this question? Or what's the value of this expression? All right, if we look at this is just a combination. It's just a nested combination. We work our way out from the inside. If we want to walk through the large rule, it says to evaluate this whole expression, we evaluate the sub-expressions. The value of the plus is just the addition operation. The value of this means we have to walk through and evaluate that combination, which, as we've seen before, has the value 7. So we have plus 7 and the number 4. Numbers are self-evaluating. There's no trick to that. So we got 7 and 4 gives us 11. All right, let's do a little bit more of an involved one here. Plus 2 times minus plus 3, 4 plus 5, 1, 2. All right, again, what's the value of this expression? Try to work it out, and then we'll work it out together. Okay, so when you're trying to solve large expressions, the general rule works. It's maybe a bit exhaustive, but it applies in every situation. So to do that, it says start with a top-level combination. What's the value of all of this? And then work through the sub-expressions. So to evaluate the entire thing, we need to figure out what's the value of this. That's addition. What's the value of this? It's 2. And then what's the value of all of this, the remaining expression? So to figure that out, we have to call evaluate on this. So that says evaluate times, and then all of this combination and the value 2. So to figure that out, we have to walk through and walk through and walk through. A simpler way, at least a colloquial way if you want, to brain your way through it if you're not trying to create a program to solve it for us, is to just start with the innermost brackets and reduce. So I'm just going to copy this expression because we're about to lose it. Just paste that there for now. And we can just do replacements a similar way to how Scheme would do it. So the innermost bracket here, this combination isn't dependent on any information outside of that combination, right? The plus isn't being added to some other combination that needs to be evaluated first. So we can just take all of that and say 3 plus 4 becomes 7. Similarly, 5 plus 1 becomes 6. Now we have 7 minus 6, which should be 1. Then we have 1 times 2, which is 2, and 2 plus 2, which is 4. Okay. And if we run our code, the last expression should be the exact same answer. So let's run it and see if it pops out with a 4. And it does. Wonderful. Think you guys get the idea there. If you want to, if you're having trouble still understanding, or if you want more practice, you can pretty much just put any random assortment of values together and then try to work your way through it. But let's do one more here, something with some booleans in it. How about, so something like or and less than 6, 7, less than 6, 7, true, or not false equals 7, 3. Okay. So again, pause it, try to work it through. What is the value of this expression? Okay, and I'm going to copy this up here to make sure we have it for later, and let's walk through a similar situation. So again, we could walk through the general rule and say, okay, to evaluate this entire expression, we need to figure out what are the sub-expressions. So we have OR is the first sub-expression, the function for ORing things. Second sub-expression is this combination, and the third sub-expression is this combination. And work through the general rule for each of those combinations, and we should come up to an answer. And again, the colloquial way of solving that is to start with the innermost brackets and figure out what the values are and do the replacements. So less than 6, 7, that's true. So we have a true here. We could do and or the not false, either way really. So not false here is true. Equals 7, 3. Again, remember this is not assignment, so it's not an error. It's just the question, is 7 equal to 3, which is false. Now over here we have and true. So true and true is true. And then we have true or false, which is also true. And then we have or true and true, which gives us true. And if we run our code again, the last example here should give us the same answer. 50-50 chance, and we got it. Wonderful. Again, I recommend just building a bunch of expressions, try and figure those out. That's pretty much it for this video. We covered the basic syntax of Scheme and the general rule of evaluation for pretty much all of Scheme as we'll see it. In the next video, we'll talk about symbolic abstraction, that is to say, hiding values behind names, or as we've come to know them in previous languages, variables. I'll see you in the next video.